Okay, so there are a few joined. So I'll let you share your screen. Okay.
Okay. Yeah, so I'll just take a few minutes to talk about some of the last few points about this LynSin. So as we talked about, LynSin was this progressive sort of more and more defined search-based method, and the last step involved this SMT-based search, right? And we said that, just using a normal Z3 or any SMT solver is probably not ideal. Here, the SMT queries that are happening are probably going to be nonlinear because there is going to be this nonlinear activation function involved. And when I say nonlinear, I don't just mean piecewise linear. I mean truly like smooth nonlinear functions, things like tan H, sigmoid, and so on. And for things like sigmoid, while Z3 can handle sigmoid queries, it's not necessarily very efficient at doing it, or as efficient as there are other solvers, but much more efficient. And there is this other problem where there are some activation functions which are not supported by all solvers, right? So like some activation functions like tan H, this is a hyperbolic trigonometric function. So this is not supported by many solvers, including Z3, right? So this paper actually focuses very heavily on using a very particular solver. It's not like this paper, they don't really say that, okay, you can use any SMT solver. They actually tune their method to this one particular solver and the features that this solver provides. So I thought it will make a little bit sense to talk about what this solver is. This solver is called DReal, right? And it's actually doesn't solve so there are a few features of this. One is that it can handle many nonlinear functions and algebraic expressions involving them. So it can handle things like tan H, or even normal trigonometric functions, sine, cos, etc. Right? It can handle all of these things. And it's actually it solves much sort of a relaxation of the SMT query problem, which is what they call the delta relaxation problem, right? So this delta relaxation problem is basically defined as follows. So we say that two real numbers, x and y, are delta close if for given delta, if their distance is less than or equal to delta, right? And what the delta relaxation problem is that it doesn't actually ask you to come up with a satisfying assignment. It only asks you to say that if a satisfying assignment exists, then this is a region, it has to be delta close to this particular real number, right? So all that it's going to give you is these delta sized regions within which satisfying assignments have to exist and outside which they cannot exist. But it won't tell you whether inside that region the satisfying assignment will exist or not, right? So specifically, what the delta relaxation
So
says.
I have one question here.
Yeah.
What is it trying to solve? Okay, now see,
Yeah.
when I say it solves d real, you said solve, it can handle tan H sine cos. What does it, I mean, obviously, what does it mean to say it can handle? Okay,
Right.
that needs to be, maybe you're going to define.
Yeah. I'm going to define. Yeah.
Okay. But you got into this delta closeness with respect to what? I mean, I didn't understand that.
Right. So so there are 2 points. Both of these I'll sort of elaborate on together.
Yeah,
because
because
I think
you have to define what the decision problem it is solving.
Yeah. That is what I'm going to do. Yeah.
I know what it is. When I say Z3 solves something, it's some arbitrary Boolean combinations of satisfiability of formulas where the atomic formula is inequality over linear real arithmetic. Okay, so that way I know what is it solving. So I'm assuming that you will define what that satisfiability problem over these functions that you have listed, tan H, sine, cos, etc. that d real is going to solve.
Yeah. That is what I'm going to define. Yeah. Okay. So let's take a step back and see what Z3 can solve. As I was saying, it can solve any sort of arbitrary Boolean combination of some atomic propositions, right? So let's write our atomic propositions like this. Fx is going to be less than 0. So in general, you can always just write it as being less than equal to 0, because whatever constant term or whatever you might have, or even not a constant term, whatever expression you might have on this side, you can always bring it to that side, right?
Yeah, but f is also limited. Okay, it is just certain arithmetic operators.
Yeah.
I don't know what you mean by fx.
Right.
So
fx
plus,
here,
minus, all, yeah, those kinds of things. So yeah.
Right. So fx here for Z3, for something like Z3, what fx is going to be some combination of plus, minus, star, division, and the variables.
Star should be only between variable and constants. Okay.
No, I'm saying Z3 can handle nonlinearity up to.
Okay.
Yeah.
Good. Yeah. So you're talking about the extended version of Z3.
Yeah. Z3 plus nonlinearity, let's say. But even that is not sufficient for what they're trying to do. So that is why they use DDL. So here Z3 deals with Boolean combinations of this form, right? So let me write Boolean combinations as this.
Give an example. Yeah, something x times y is less than minus phi, or x divided by y is greater than something. Correct? Yeah,
right. So for example, maybe I'll put the example in a different color. So let's say that x plus y is less than equal to 0, or xy is greater than equal to 0, and xz is greater than equal to 0. Right? So something like that. See, each one of them is basically some expression. So this will be less than equal to both of them, because that's the convention that we're following. So each one of them is going to be some expression less than equal to 0. And then the expression is going to be, some involving plus, minus, star, and so on. So maybe an even more aggressive example would be something like x minus y by z is less than equal to 0, right? So each expression is going to involve plus, minus, star, and so on. And you're allowed to do these Boolean combinations of that expression less than equal to 0. So each atomic term is going to be expression less than equal to 0, and then you're allowed Boolean combinations of that, right? And that in general ends up looking like this, right? Okay. So now what DDL does is DDL allows you to do two. So there is one sort of two modifications to this decision procedure that DDL does. So for DDL, Number one is that these expressions can contain more complicated functions, like, and DDL's website produces a list, has a list of all the functions supported, but I'll give you some examples: sine, cos, log, exponential, tan h, and so on. Right? It supports a much wider variety of functions. So now immediately you're allowed to have expressions like this, where you can say sine of x is going to be, and again, I'm using less than equal to 0, right? Sine of x is going to be less than equal to 0. And cos of xy is less than equal to 0. Or log of x minus y by z is less than equal to 0, right? Or even, it's not like the sine, cos, or log has to be the outermost function. It can be something like log of x minus y times y by sine of z. You can think of complicated expressions like this. Any such expression is now allowed, right? So this is number one. Number two, so here now, concretely speaking, our expressions or our the formulae over which we're doing a decision problem is a conjunction of a disjunction of Fij x less than equal to 0, where Fij x is an expression with plus minus star division variables and all of these things.
Yeah. By the way, Z3 even allows negation, which means if it's less than or equal to 0, you can also get greater than 0.
Yeah, definitely. So the moment you allow something like minus, then you can, of course, convert any expression to this form. So I want to point this out if this is not clear, that this is, if you have something like an expression like this, a plus b by c is less than equal to d, you can, or say d plus e, you can always convert this to a plus b by c minus d minus c is less than equal to 0, and so on, right? So this is a form into which you can convert your expressions whenever you want, as long as you have the minus operator. And even Z3 allows you the minus operator, and DDL, of course, also allows you the minus operator. Okay. So the first modification that DDL does is that now each one of these Fijs, which previously only had these, are now also going to have these, right? So is this clear so far?
Yeah.
Okay. Now here's the second modification, where all of this business of delta closeness comes in. The second modification is that I think I might be taking too much time here. So the second modification is that you're going to relax this expression of is being precisely less than equal to 0 to it being less than equal to delta, where delta is going to be some constant, right? So you're going to say now that your problem or your query is going to look like, again, all possible Boolean conjunctions. And again, these Fijs are going to be these complicated expressions involving these complex functions. But now you're only caring about whether it's less than equal to delta, where delta greater than 0 is some fixed real, right? So they are only going to satisfy this, and these only going to check the satisfiability of this. And when DDL comes up with a satisfying assignment, that assignment is not guaranteed to satisfy all of these, but it's only guaranteed to satisfy the relaxation where you're replacing 0 with delta. Okay. And what they say is that this DDL.
No. Here is delta something the user given delta?
Yeah, so the user will have to, so when you configure the solver, you'll have to specify what delta you want to use.
No, but once at the top level.
Yeah, once at the top level. You cannot have different deltas for different.
But delta itself, because see, if you put it this way, I mean, I can always move the delta to the left side and then make it into something that is within the syntax. But what you're saying is this delta is like a meta variable. Okay?
Yeah.
Okay, it's not part of the language.
Right, it's not part of the language. And the important thing is that, while you can move it into that side, but you cannot always convert any expression for, so for example, if I give you the expression, say x by, or let's say x by y is less than equal to 0. I cannot very easily convert it into a form where it looks like x by y is less than equal to delta. Right? Like, it's not true that if I have a satisfying assignment of this, I can get back a satisfying assignment of this. But the other way around is true. So if I have a solver that can solve expressions of this form, of course, it can always solve expressions of this form, because I can then just say that, I'll solve for x by y minus delta is less than equal to 0. But if I'm only allowed x by y is less than equal to delta, then I cannot easily convert it back into an expression of this form, right? So like, I cannot easily convert an expression of this form into the delta relaxed form. Like, if my solver can only handle delta on this side, there is no way of converting this expression so that it has delta on this side and means the same thing, right? So,
well, I don't know. I mean, because you allowed the maybe we're going into different things, and I don't want to stop you, because I can make delta if it's a constant, then I can always, the language allows x by y minus delta. So x minus y by x by y minus delta less than or equal to 0 is the same thing as x by y is less than or equal to delta.
Yeah. So that is going from this side to that side, right? So I'm saying going from here to here is fine, but the other way around is not, right? Because if I give you this expression, then how will you convert it into an expression of this particular form, right? Because remember, the solver expects this. Correct? You can say something like, for example, x by y plus delta is less than equal to delta, and pass it to the solver. But then a satisfying assignment for that will not be something where it's, like less than equal to 0, right? So what I'm trying to say is that this delta relaxation is a one-way operation. Like, you can, like, if you just because you can solve the delta relaxation of this, it doesn't necessarily mean that you can solve the original problem as well, right?
Sure, if I understand. So if I solve to the original thing, if I give x by y minus delta less than or equal to 0, and if I find the solution, that one is a solution to x by y.
Yeah. So if you can solve the original thing, you can solve the delta relaxation, right? Yeah. But if I can solve the delta relaxation, that doesn't mean that I can solve the original thing. So you can't go this way. This route is not allowed, is what I'm saying. So for example, like if I have a function like this, which is asymptotically approaching 0, right? So here, the original SAT problem, so I just have a single function f, and I'm asking whether f is greater than or equal to 0. So this is unsat, right? Because it's asymptotically approaching 0, but it never really touches 0. Whereas the delta query is now going to be.
Yeah. I mean, I understand. Okay, I guess do you understand? So I think the basic thing is delta is above. Okay, so you will have to, you can't make it as part of the language. That's all. So if you make it as part of the language, and then it allows, then both sides are possible. I think the Jyotis have. Yeah. Okay. Go ahead. Yeah. I think I.
So is it clear to everyone?
Yeah. At least the Jyoti is saying yes.
Okay. What about the others?
Are you guys in the same room?
Yeah.
Huh?
Yeah, I think someone else also said yes.
Oh, Drupjyoti says everyone knows, sir. He says, what is that? It's not clear. Does it mean it's not clear? The no answer was for different people at the time. Yeah.
Okay.
Yeah, I think your asymptotic thing made it clear to me. Okay, because the delta is kind of outside the framework.
Right.
Solve it up to a certain kind of thing, and then you can make delta smaller and smaller and smaller, and you can get to that.
Right, you can get more and more accurate things. But there are functions where delta sat, the delta relaxation will always be sat, whereas the original thing is always unsat. Because, for example, in this asymptotic case. So that is something that we are giving up. But what they say is that, so one of the things that the DDL, there is a paper for DDL as well. One of the things that they say is that this problem, this delta relaxation, is decidable. And the way that DDL operates or way that it solves is by doing branch and bound, right? So initially it will do an interval propagation. So if you have a really huge function, let's say, initially it will do some, so they'll say that this is the function that I'm trying to see whether it's, delta close or not. So initially it will do some interval propagation. It figures out that, okay, this function is, so let's say my delta is something like this, right? So after the initial interval propagation, it figures that, okay, the intervals actually intersect delta. So the interval is of this, or the range of this function is between here and there, and it intersects delta. And this interval propagation may be over approximate. But then what they'll do is they'll split the domain into two parts, and then do interval propagation only on this domain, and then interval propagation only on this part of the domain, right? So now they know that, okay, only this interval intersects delta. So now they'll split this interval into two parts, and then do interval propagation on those two parts again. And again, they'll only pick the ones that intersect delta and then go on like that. So in this way, they'll do a branch and bound. And this branching and bounding basically will slowly let shrink the interval smaller and smaller and smaller. And eventually they'll have such a small interval where by looking at the function, they know that this function has to either intersect delta or not, right? So eventually when the delta interval is really small, they'll just return that, okay, this is the small interval in which there might be intersection. Otherwise, they'll say it is unsat, right? So in this sense, it will solve an over approximation of this. Because if at some point while splitting the intervals, it finds that no one ever intersects delta, then it means that no one actually intersects the zero as well. The function doesn't intersect the zero line, and you're done, right? Whereas if it keeps branching and bounding and finds that, okay, there is a delta intersection here, there's a delta intersection here, and so on, at some point when the size of the intervals themselves are smaller than delta, it will return that small cell as your quote-unquote counter example, and it will basically stop the search at that point, right? So this branching and bounding based method, it turns out that for these kind of queries is very scalable, and it actually lets this LynSin paper to make multiple SMT queries and adjust delta, and then make one more query, adjust more delta, and so on, right? And so in this way, they have chosen this DDL to suit their particular problem in terms of the query. The other thing is that since we're solving a delta relaxation, remember that, so this VL over here represents the shift that we were looking at earlier. remember that instead of getting a proper bound where we are saying that, okay, what we wanted is that some Vxi plus whatever shift, right, should be less than equal to 0. Instead, what we have is that it is less than equal to delta, right? So, sorry, I meant greater than equal to 0. So we wanted this function to be always be greater than equal to 0. Instead, when we have an unset, what we know is that it is greater than equal to delta, right? So then what we can do is we can push this delta here and add this delta to the shift itself, right? So if we know that this Vxi greater than equal to 0 is delta sat, Vxi plus shift, whatever shift, let's call it S, is delta sat, that means that, sorry, delta unsat I meant, or delta valid, let's say. That means that this is going to be valid. That means that Vxi plus shift plus this minus this delta is going to be greater than equal to 0, right? So you can shift this delta to this side, include it in your expression, and that way you'll get something that is going to be a valid upper bound, and you can find a tight shift for your function, right? So in this way, by controlling the configuration of the DDL solver, they can control the size of the delta, and this size of the delta will tell you how strong of an upper bound you get. And if you make delta large, then DDL will be, it will return sat or unsat for your query really fast. But it will also mean that your bound will not be very strong. Whereas if you make delta very small, you will have a very tight bound, but you'll take more times finding it. So this again gives us a sort of a precision performance trade-off that we can utilize. Like if we can initially try to verify the network with some loose bounds, and if that fails, we can slowly try tightening these bounds. So, and we don't want to initially try a very tight bound because that will take a long time. Maybe a loose bound is good enough. But if we slowly try tightening it, as looser and looser bounds fail to prove as the thing, maybe eventually at some point.
As a user, do I have to muck around with this delta?
Yeah, you can sort of configure this delta.
Or do I not need to?
You have to specify a delta when you configure the solver for query. And then when you specify the delta, the solver will only give you the sat or unsat result based on the delta that you have given, right? So as a user, you pass this delta once at the top. So as a user, you will pass this particular delta once at the top.
That is for DReal. I understand that.
Oh no, for LynSin you don't. LynSin they actually
Okay, so this is only a detail which we may not
we may not care about.
As a LynSin user.
As a LynSin user, you don't have to worry about the delta. LynSin has its own heuristic, like sort of own list of values of delta that it tries essentially.
Okay. So this is just a detail that you are just explaining as a matter of giving a little bit of insight into how it's.
And I think that it's like in terms of like understanding how it works, this is kind of, I feel like an important detail, the fact that they're using this specific solver. Because it not only allows them to make these queries, like solve these queries in a scalable way, it also sort of leads them to another precision performance trade-off, right? So as a, like, in that sense, it is something that, we can like it's a key aspect of how this algorithm works.
How it works is yes, but as a user, we don't have any control over it.
Yeah, as a user, we don't have any particular control over it. So LynSin will only give you some list of values of delta it has, and it will try those in some sequence, right? But it tries to, within that list, sort of find the best possible value of delta, right? So essentially, LynSin essentially performs a search over the deltas again to try and find the best possible value. So instead of doing a search over the shift, it actually what it does is a search over the deltas, which is a slightly different thing. And it tries to find the smallest sort of delta for which you'll get an answer. Sorry, the largest possible delta for which you get an answer. And that will give you the smallest shift. So this is what this is how this this is all I had to say about LynSin. So any questions so far? Any questions at all about LynSin?
Yeah, but I think you should kind of give a refresh the thing as to what was the original problem you were trying to solve. So you have all this tan H and everything.
Mm-hmm.
Okay? So your original
right. So maybe I'll go over
was so you could throw in activation functions,
which are really complicated expressions,
which
right?
are really complicated expressions involving all these complicated tan H, sin H, etc.
Right, exactly. So for example,
those things, what it will do is so it will derive what? And it will derive some
linear upper and lower bounds. So for example, consider this, right? So this x times tan H, some random. So say for some whatever reason you want to use this as an activation function, right? So let's say that the neural network comes with this as an activation function. So now what this allows us to do is this, if you just ship this into LynSin, and you'll also give LynSin the interval within which you're interested in linear upper and lower bound, and LynSin will automatically find a tight linear upper and lower bound. So LynSin will tell you that okay, there is some C1x, C1LX plus C0L less than equal to sigma x less than equal to C1UX plus C0U for all x belonging to L, U. LynSin will give you this as a condition. And the way it does that is that it will basically, firstly, it will do some sampling, some coarse sampling.
Yeah, but that you explained.
Yeah. So that flowchart I had over here. So it will do a coarse sampling and LP, and then a fine sampling to minimize the shift, then SGT to minimize it further, and then the SMT based search to minimize it even more. Right. But this is basically what LynSin will do. And having this means that you can fit it inside deep poly, because remember in deep poly or any deep poly like algorithm, the way you handle an activation function is by basically deriving bounds of this form, right? So in deep poly, you'll have a step where the only step which depends on what your activation function is the step where you derive bounds of this form from the concrete interval bounds. And LynSin says that, okay, we can sort of, instead of you having to devise that step precisely for each possible activation function you want to use, we can sort of automate it. No matter what the activation function is, just throw it in and I'll give you the bounds. So that is what LynSin tells you, or allows you to do. And another thing is that this LynSin actually allows even activation functions involving multiple variables. So you can actually devise a node which has an activation function defined by sigma of x1, x2 is equal to x1 star x2. And LynSin will find a linear upper bound and lower bound for this, which is, tightest given your intervals, right? So it will actually find a linear upper bound and lower bound that is tight given the intervals for x1 and x2. So it will find lines bounding this nonlinear, so bounding this multiplication given where your activation region is. So for example, if you imagine the x times y, if we graph it, it might look something like this, right? So it's 0 when either one of them is 0, but as either one of them increases, this guy also increases, and there will be higher and higher bumps and so on, right? And if you know that your two inputs lie in this interval, then LynSin will automatically give you a very tight linear upper and lower bounds for this. Whereas if you know that you know all you can say is that it lies in this huge interval, then LynSin will still give you some bounds, but they won't be as tight because of the non-linearities involved. But the point is that what this allows you to do is that as your intervals, as these intervals get smaller, you're going to, or you're guaranteed to get better and better, tighter and tighter linear bounds for the deep poly algorithm. Right? So is this all okay?
Yeah, I think you have to have them give some examples that they can work on, because otherwise I think this, I mean, guys, do you have any questions? Okay. And also you have to set, we'll have to, I think, set the context right, where they might use this. Okay. And
yeah, so I want to ask, is the question, or is the context within deep poly in which LynSin may be applicable, is that clear to everyone?
Yeah.
Okay, so can you just say what the context is?
So we are here. So since we are involved in complex activation functions like tanh and etc. So we need to Z3 directly can't solve those. So we are using the LynSim algorithm gives us the linear upper bounds for these activation functions. Like you have written a complex activation function. So for that, it will give like upper bound and lower bound.
Yeah, and it's not that Z3, like, I mean, Z3 can never give you an upper bound and lower bound, linear upper bound, right? Like, it's not like Z3 can solve even simple activation functions. It's just that for simple activation functions, we had some, special, so for each activation function, we had one special algorithm for finding these bounds. That is what deep poly sort of used, right? Whereas here, we are going to say that we're going to automate it and we're going to be able to find it for any complicated function, right?
yeah, that's right. But you will have to invoke LynSim inside deep poly, or already integrates. LynSim does not integrate deep poly, does not have that layer. So
no.
You'll have to use deep poly, and from inside deep poly, instead of deep poly by default does it for ReLU. So in that, as one of the steps, you have to invoke LynSim, correct?
Yeah, exactly.
So, but is that support available, within deep poly?
No, so by default, not. So what the LynSin paper?
Okay, so that would be now. So if it is not available, so that is what I meant. The context, so that is so that integration of deep poly and LynSim is.
So that is something that actually the authors of the LynSin paper did in their implementation. So what they did is that they took deep poly and they modified it so that it supports, in general, any such plugin for finding linear bounds. And
which means if they use their tool, then it is already integrated.
Yes.
Okay.
So their tool is an integration of these two things.
But that tool is not called LynSin.
So no, only a part of that tool is called LynSin, which is the part that. So what they did was, in terms of the implementation, they did two things. They modified deep poly so that LynSin may be integrated, and of course they implemented LynSin itself.
Yeah, so they have an implementation. Is that available? So for the class, what is it that we want them to use? Okay, I mean that is you have to give clarity on that. Okay.
Yeah. So
I mean, is that implementation of that the team? I mean, the authors, whoever of this paper, is that tool made available? Is that what we will be planning to use?
Yeah, the tool is available, and so is deep poly, and yeah, I think we can use that for the project.
Okay, and yeah, a little bit about the. Well, I think let's reserve the discussion about the project. I mean, I think what we should do is, have them, there are lots of tools that we have talked about. So I don't want them to get intimidated or confused and so on. So they're already using Reluplex and things. It will be a mixture of these tools. Don't get scared, guys. I mean, there will be in the context of the project. We want you to solve some significant. It has to be something significant that will also allow you to exposure to these tools. We figure out a way how you could productively and in an interesting way use all these things together to solve something that is that is interesting. Okay, so but before then, just like you had the opportunity to solve some simple problems, maybe we should also give them as
yes, so definitely the deep poly tool is something that can be used directly, so we can maybe give some simple problems.
Yeah, but the deep poly, but this LynSim integrated under deep poly, that we don't have now.
Yeah. But that will have to sort of. I don't think that is something that we can give an exercise about. But
but that is why I asked. So you said that the authors have implemented some version in which they have integrated this LynSim inside deep poly, but that is not available for distribution, correct?
No, so it is available for distribution, right?
But then they can use that, no?
Yeah, but I don't think it is. So I think that it's sort of like a prototype implementation, which I'm not.
So it's a research tool that they cannot use. Okay.
Right, but there is a very good tool for deep poly called ERAN, which is maintained by ETH Zurich, and that combines deep poly and several other deep poly developed into some of the algorithms, which I think all of them are implemented in there. That is something that we can use, and that is something that we can use as a black box as well. So for the project, I think that is all that we will need.
So there is another tool, is what you're saying. Okay.
Yeah.
Which we can do. So once
and I'll give maybe an exercise on that.
Guys, so maybe that we can have them as part of the warm-up thing for this is the roughly this is a plan. Okay. So by next Wednesday's class, we will have the project scope defined. Guys, this is what I'm saying. So that's what we are working on, and we will have some as part of that. As a warming up to that, as a first step towards the project. Okay, some using these, getting you acquainted with the tools that you will eventually be experimenting with and will be using as part of the project. Okay, so that will be the first step. While we will be talking about the project, there will be some small exercises for you to get warmed up and acquainted with the tools, as part of which hopefully that we will have this LynSim deep poly integration made possible for you. Is that as a plan? What we can, I mean, the reason all these things that is allowed is because so we are just also getting aligned on these things.
So in terms of the plan, I think, sir, what we can definitely see is that there will be one sort of warm-up exercise on deep poly itself, which is via this tool from ETH Zurich, and then we can go on to integrating LynSin and deep poly. And so we don't need to really do an integration in the way that they have done in their paper for the project. We'll have some way of our own to do this integration.
So that is a little bit programmable, is what you're saying.
Yeah.
Okay. So so is this a proper time to?
Yeah. If nobody has any questions, then I'm done.
So don't get scared. Okay, so we will, even if you can't think of all the questions, as as part of the idea is to start getting you to start working on the project starting next week itself, so that as part of that initial effort, all these getting acquainted with the tools, etc., will help you out. Yeah.
Yeah.
Okay, so I think I'll stop sharing now. So that,
Okay.
yeah, so you can take over.
I'll take maybe 15 minutes, or even if I'll make sure that I end it. So I'll have to share. Okay, so I want to keep it a little bit open. Do you have any? Okay, so is this visible? Maybe I'll make it.
Yeah, it's visible to me.
Yeah, I know it's visible. Forget about these things. Someone has some questions. The font is a bit small, but how about now?
It's visible.
Okay. So first thing is, I guess there was some questions, okay, about. Okay, so I will get to those specific things regarding. See, there is, all these valid things where for question.
Yeah, it'll be Q1 2.2 and then Q2, Q3, Q4.
Correct. Q1 2.2. I treat this thing as implications. Okay, so that's what I wanted. I actually wanted this to be, say validity is always converted into unsatisfied negation of it. So I meant to have it as A implies B is verified as unsat. Validity of A implies B is verified as unsat of A and not B. So treat this as, you could solve this for both valid A implies B and valid A B. For question 2, 3, 4, as well as here for this 2 valid, you treat them as implications. Okay, valid of this implies that. Okay, so that is the clarification, okay, that I think some of you probably had, and that's what I meant to have. If you have, I don't know if you've already worked through your problems. You can take more time if you wish, and even if since I made the announcement only today, even if it means that you want to submit it, although I've said Friday is the submission date, I'm not going to be that strict, so you can take till the weekend if you want more time on it. So does that answer at least the question that some of you had? I don't know who asked that question, but
Yeah.
Okay.
So I think Dhrubajyoti asked that question. So
I see. Okay. It's fine now. Yeah, but one thing that I wanted to, although I know you have not asked this question, what am I doing with? Why did I make this question 1, 2, 3? Okay, I want to maybe spend a little bit of time, although you did not ask that question for my own this thing. But no, but there was this question, I think, on last Marabou tutorial. Who was there was only one person who came there. Was it Drupjyoti who was there last week?
So Drupjyoti is saying Nabin asked the question.
Nabin. Okay, so that's Nabin. Okay, so that was a very interesting question. Okay, Nabin asked the question that why Reluplex or Marabou or Reluplex, and why not Z3? Okay, to perform DNN verification. Okay. Or more specifically, what is the potential advantage that Reluplex can offer? So the motivation for my making these three questions was, hopefully while you work on that, that will shed some light on that question. And that's what I want to talk a little bit about. Okay. So that's why I made you work. One of the questions was on simulating the offline algorithm, okay, on the simple example, the running example that I'm using, and answering a few questions that shed some light on on the complexity of this problem, which answers this question. Hopefully Reluplex will be better. So how does offline algorithm work? If you notice, as you work on this problem, you will recognize it generates first, it creates a Boolean abstraction, okay? And then of the formula that you want to solve, the first order formula over linear real arithmetic. So there is a Boolean layer on top of that, right? It's an arbitrary Boolean combination of these inequalities over real arithmetic. So first it generates, it consists of Boolean abstraction, then it generates a satisfying instance, say mu, of the Boolean abstraction of that formula. A satisfying instance. Now that satisfying instance is a real satisfying instance for the original formula, and that needs to check as long as it also satisfies all the real arithmetic constraints, for which it makes a call to an LP solver to check if that satisfying instance is feasible. Therefore, a measure of complexity, Z3 basically uses this. It doesn't use the offline algorithm, but that's why I presented that thing as a naive solution. Z3 is a lot smarter, okay? It integrates this LP solver with the Boolean abstraction in a more intimate fashion, to get better performance. But as a first cut, it is okay to do treat that Z3 is doing using the offline algorithm. So the measure of the complexity, one measure could be the number of LP calls, okay, which itself is dependent on, because each time it gets a satisfying instance, the Boolean abstraction, it has to check if it is feasible using an LP call. If it is not feasible, then it has to generate a new different satisfying instance of the Boolean abstraction. So you go back and forth, okay? So eventually, it will make multiple LP calls in the process of finally arriving at a satisfying solution to my original formula. So a measure of complexity is the number of LP calls, which itself is dependent on the number of satisfying Boolean satisfying instances that you will have to consider. So that's why I'm kind of asking you in one of the problems to check on the number of LP calls in the worst case that it will have to end up doing. Okay, so that will give you hopefully some insight into the So each time, I mean, if you are lucky that the first satisfying at the Boolean abstraction level that you make happens to be a feasible instance, then you get lucky, and then you can end up doing one LP call. Otherwise, depending upon the decisions on which you try, get how you enumerate this satisfying instance, the Boolean level, you may end up having to make more number of LP calls, and that is what that's the kind of the measure if you were using the offline algorithm. Okay, and that that is the purpose, and I'm hoping that you will get an idea in solving that what for that simple problem, what the worst case and the best case might be in terms of the number of LP calls. Okay. Any questions there? Okay. So now, how does ReLU? This is once. Okay. There's some question. Okay. Good. How does ReLU work? Okay, the same kind of complexity measure in terms of number of LP calls can be used, but there is a small twist in the case of ReLUplex. And if I go back, this is just a summary of recap of how ReLUplex works. See, ReLUplex itself has two phases, and it'll once I go through it, it'll address Naveen's question that Naveen raised. Okay. In phase one, ReLUplex generates a satisfying solution of, and it tries to solve an LP instance, which is an over-approximation. That is an over-approximation of the original DNN. It constructs an LP instance of the original DNN, because the original DNN is not an LP instance, the model of the original DNN, because it uses ReLU. Okay, and it throws away some of the ReLU constraints and constructs an LP instance, and that it solves. Okay, obviously that if you're that whatever solution that it produces has to also satisfy all the ReLU constraints. So it has to do a check, okay, that whatever satisfying solution that you the LP on the over approximated model, you will have to do so it will go through, it will try to see if all the ReLU constraints are met. If not, it will fix them, and then it will make because in the process of fixing, you could have broken you might have in the process of fixing the broken ReLU page, you could have violated some of the LP constraints, and therefore it has to repeat this. Okay, and that is in phase one. So that's why. So what factors impact this complexity? I mean, the SAT solution that you generate, okay, because there could be several different SAT solutions for the over-approximated model. And there is also, how you fix the ReLU pair. You remember that there are two rules, update FOB. You can either change the forward variable and the back variable in the ReLU pair to fix the broken ReLU pair. And and more importantly, whether there is some common satisfying solution independent of whether the ReLU constraints are ReLU nodes or active or inactive. Okay, all these factors influence in how many iteration. Okay, each iteration requires an LP call. Each iteration, phase one, requires one LP, and that's why so you will require number of LP calls here, and after that, so if it is not, if phase one doesn't converge after a certain number of iterations, you're not able to fix any of the ReLU pairs, then it goes into phase 2. So the complexity of the phase 1, the amount of effort that you have put in phase 1, can be measured in terms of the number of LP calls. But there is also a phase 2 in ReLUplex. There, what you do is, if in ReLU the phase 1 runs out of steam after a certain number of iterations, then it will split. It will split on one of the ReLU conditions to consider the active, inactive cases. Okay, and each time you do that split, you will have to invoke the ReLUplex algorithm, which includes the phase 1 on each of those 2 instances, and therefore the overall total number of the number of splits that you will have to do is also a measure. Okay, now they sometimes without splitting the you may be able to get a solution that satisfies without actually doing the split. Then you will you can win over the offline version, over Z3. Okay, but if the number of splits that you will have to do will end up a lot, then then you will end up ReLUplex may not give you any kind of advantage over the thing. But generally, so this is where, without actually, by delaying the split, so that's why trying to measure the number of splits that you might require, as well as the overall number of LP calls, is also a measure. And that itself, as I said, will depend on how successful ReLUplex will be in getting a solution in phase 1 itself without actually having to do the split, and that will depend on these factors that I have listed here. And therefore, when you simulate the ReLUplex, that is one of the questions. Question 3, I think, is asking you to do that. Okay, on the ReLUplex algorithm, you will have to, when I say, okay, try to do, try to get a strategy by which you can get as, make ReLUplex work as efficiently as possible, you will have to explore these factors, which you might have already figured out. Okay, but I thought I'll mention that, okay, as motivation for why I have given this. And we'll after you have submitted your solutions, then we will revisit this to see if you have learned this, you have a satisfactory answer for yourself for the question that Naveen raised. Okay, so in the worst case, both algorithms might end up performing the same way. But in ReLUplex, if this third factor that I've listed here succeeds, and then you can get phase 1 itself to succeed in finding a solution without any case splits, or you use phase 2, the case splits will be as minimum as possible, then ReLUplex will win over generally Z3. But for any specific thing, it is not necessary that one should be always superior to the other. Okay, so that's where I want to end. Yeah, so if you have any questions, or hopefully you will get some insight into some of the points that I've made in the process of your working on those questions. Okay, so you have any questions? Okay, so then, okay, yeah, so yeah, I'll expect you to turn it before Monday, so you can take the weekend and then submit your solution, yeah, before Monday.
Yes, yes.
Okay, thank you.